Welcome back to another session. In this session, we will discuss external viscous flows. So, we will consider a situation where you have a flat plate which is aligned with the direction of a uniform oncoming free stream. So, the upstream conditions are known. Let us say this velocity is u infinity, and you want to find the velocity distribution over the plate. Now, another typical situation could be say flow over a cylinder. And again we will consider a case where the upstream is a uniform flow. Now, another typical case for which exact solutions are available is flow over a wedge which is symmetrically placed with reference to the upstream flow. So, you have a streamline which is a line of symmetry, and you have fluid going upwards and downwards. So, this is a wedge, this is a cylinder, this is a flat plate. So, we will consider the first case in great detail, and if you have time I will touch upon the other cases. So, we will consider a plate of infinitesimal thickness, and we will choose a coordinate system with origin at the leading edge. So, this is the origin, this is x, this is y, and the upstream flow is in the x direction. So, the plate is y equal to 0. Now, the governing equations have already been derived by Professor Chakraborty. So, I will simply write them down. We will consider a case where the flow is steady and 2D. Now, this will occur when the length of the plate in the z direction is very large, typically infinite. So, the velocity field for such a flow will be of this form u of x y I plus v of x y j, where I and j are the unit vectors in the x and y directions. So, we have two components of velocity and they depend on two coordinates. It is independent of z because it is 2D and it is independent of time because it is steady. Now, the pressure also will be of this form P of x y. So, first of all I write down the equations in vector form. You are going to have the continuity equation for incompressible flows, which is simply divergence of V equal to 0, and then you have the momentum balance, which for a Newtonian fluid is your Navier-Stokes equations. So, for constant density constant viscosity case, you are going to have rho dV dt is equal to rho g minus grad p plus mu Laplacian of V. So, these are the Navier-Stokes equations. For constant density, a constant viscosity, incompressible flows. Now, first of all I will define a term which you may call piezometric pressure. Or some others simply call it a modified pressure. So, to motivate this, let us look at the gravitational acceleration g, which is a vector. It can be written as g x I plus g y j plus g z k, where g x, g y and g z are the components of this vector g in the x, y and z directions, and this depend on your choice of coordinate system. Now, consider the position vector of a point r, which is x I plus y j plus z k. Now, if you consider the quantity say g dot r, this will be g x x plus g y y plus g z z. Now, if you look at del del x of g dot r, you are going to have g x del x plus g y del x plus g z del z del x. G x, g y, g z are constants, so they can be pulled out of the derivative. Now, since y and z and x are independent coordinates, these two terms are 0 and del x is 1. So, this is simply g x. Now, similarly, if you look at del y of g dot r, you are going to have g x del x del y plus g y del y plus g z del z del y. Now, once again two terms are 0, these two are going to be 0 and this is going to be equal to simply g y. Now, if you look at del z of g dot r, it is going to be g x del z plus g y del y del z plus g z del z del z. The first two terms are going to be 0 because these are independent coordinates, and the last term will be g z into 1. So, you will get simply g z. Now, recall that the grad of a function f is del f del x I plus del f del y j plus del f del z k. Now, if we take this function f to be g dot r, then you see that grad of g dot r, which is a scalar, is g x I plus g y j plus g z k. Since if you go back and look at what we did in the previous slide. The x, y and z gradients of this function g dot r are g x, g y, g z. So, this we can nothing but the gravitational acceleration. Now, consider these two terms rho g minus grad p. These are the two terms which occur on the right hand side of your equation. If you look at the momentum equation, the first term on the right hand side is the body force per unit volume, which is rho g. The second term is the net pressure force on the fluid particle per unit volume, and the third term is the net viscous force per unit volume on the particle, and the left hand side is the mass times acceleration per unit volume. Now, let us look at the first two terms on the right hand side, rho g minus grad p. This now I can write as rho times grad of g dot r minus grad of p. Now, we will consider cases where the density is constant. So, if rho is constant, then rho g grad g dot r can be written as grad of rho g dot r. This grad is a differential operator. If rho is a constant, you can pull it inside. So, under those conditions, rho g minus grad p can be written as grad of rho g dot r minus grad p. Now, grad is a linear operator. So, I can write it as grad of rho g dot r minus p. Now, if I define a quantity which I will call capital P, which is say small p minus rho g dot r, then you will notice that this term is minus of capital P. So, we come up with this expression that rho times g minus grad of small p is minus grad of capital P, where capital P is small p minus rho g dot r. This is true if rho is a constant. Now, you may recall at this stage the basic equation of fluid statics. Which is rho g minus grad p equal to the 0 vector. Now, you may recall that I had mentioned earlier that the basic equation of fluid statics is a special case of the Navier-Stokes equations for cases where the velocity is 0 at all points and all times. In that case, the first term is going to be 0 and the last term is going to be 0, and you are going to have 0 equal to rho g minus grad p. So, this expresses the fact that there is a balance between the body force and the pressure force, net pressure force on the particle due to the pressure distribution on the surface of the particle. Now, this I can now write as minus grad of capital P equal to 0, which means that grad of capital P is 0. So, P is a constant. This result we had derived earlier. So, it means that P minus rho g dot r, which is your capital P, is a constant when the fluid is at rest. If rho is constant and V is 0 everywhere. So, that means P is rho g dot r plus constant. This is the result which we have derived earlier. So, this quantity P which you have over here is what you call modified pressure by many authors, or some people call it piezometric pressure. So, if you have a constant density fluid which is at rest, then this piezometric pressure will be a constant at all points. Now, why are we doing all this when we are talking about viscous flows? Well, if you go back to the Navier-Stokes equations, I will write it in this form: rho dV dt, which is acceleration, is rho g minus grad p plus mu Laplacian of v. So, this then we can write as minus grad of capital P plus mu Laplacian of v by introducing this capital P, which is the small p minus rho g dot r. So, now you have one less term on the right hand side of the equation to deal with, that is the effect of gravity has been clubbed with the effect of pressure. So, this is a form which we will use to find the solution for the flat plate. So, now let us consider the flow over the flat plate of infinitesimal thickness, and we have an upstream condition where the approaching fluid is a uniform flow with some value u infinity, and we will take a coordinate system as I said earlier with the x along the plate, y normal to the plate, and the origin at what is called the leading edge of the plate. Now, if you have a finite plate, this edge is called the trailing edge. Now, if I write down these equations for the 2D case, you are going to have rho u del u del x plus v del u del y equal to minus del p del x plus mu into del 2 u del x squared plus del 2 u del y square. This is your x momentum equation or balance of momentum in the x direction. So, it represents the x component of this vector equation which I have written on top. This dv dt term, if you expand it, there are 4 terms, but 2 of them are 0 because it is steady and 2 dimensional, and del p del x is the x component of grad p, and this quantity here is the x component of the Laplacian of v for 2D case. Similarly, you can write the balance of momentum in the y direction, or we will call it simply the y momentum equation. So, this is the y component of the Navier-Stokes equations. So, you are going to have rho times this operator u del x plus v del y. This is a v dot grad operator now acting on v equal to minus del p del y plus mu del 2 v del x squared plus del 2 v del y squared. Now, you see that in this equation you have derivatives with respect to u, v and p. So, there are 3 unknowns which you must determine by solving the equations. One is u, one is v, other is your capital P. So, you need 3 equations. So, the other equation which you can use is the continuity equation or differential equation for local conservation of mass. If you have an incompressible flow, that is simply del u del x plus del v del y equal to 0. So, these are the 3 equations which you can solve with appropriate boundary conditions. You have to make sure that the velocity field is such that u and v are 0 on the plate, and as x goes to minus infinity, that is far upstream, u should go to u infinity, v should go to 0. Now, as you can see, these are coupled nonlinear equations, and it is not one equation, you have a system of equation, and it is not easy to solve. Now, what we will do is we will do an order of magnitude analysis and try and estimate before we solve the equation that which terms of the equation are important and which are not. And if we find that certain terms in the equation are small compared to the others, we will neglect those terms and try and solve the simplified equations. Now, before we do that, I will take an integral approach and get an approximate solution. So, here we will take a control volume, and the control volume analysis has been covered by Professor Sohm. So, we will see that here to get an answer we have to make certain assumptions. So, later on I will come back to the differential equations and justify those assumptions, but this is easier to do. So, I will do this first and then we will go to the more complex things. So, let us say you want to find what is the drag on a plate. Now, I can do it in several ways, that is you can choose different control volumes. So, I will first of all give you an indication. Suppose there is a plate, you can choose a control volume with one surface which is coincident with the plate. So, this I am indicated by dotted lines. So, one of the surfaces of the control volume has to coincide with the plate if you want to find the drag on the entire plate. Now, you can take a rectangular control volume and apply your conservation of mass and momentum to this control volume. Now, another way to do it is take a control volume again with one surface which is coincident with the plate, and the other surface which is not rectangular, but we will consider the top surface to be a stream surface. So, this surface we are going to say will coincide with the streamline, whereas this may not. So, you may have a velocity vector here which has a x component as well as a y component, if this is x and this is y. Here the velocity vector is tangent to this surface. So, there is no mass flux across this surface. Now, before we go into the analysis, I will sketch a typical profile which you might get from experimental observations. So, if you look at the flat plate, let us look at this section over here. You will see that the velocity, which if you look at the x component velocity, it is going to be uniform with a value equal to the upstream value u infinity if you are far from the plate, and at the plate the velocity will be 0 because of the no slip conditions, and then you are going to have a sharp gradient close to the plate and it will go up like this. So, if I show the magnitude of the velocity by these lines, this is what is called a velocity profile, and typically we put arrows here to show the direction of the flow, but you have to keep in mind that this is not the direction of the velocity vector. Okay. Do not get the impression that the y component of velocity is 0. So, that may be a common mistake. Okay. These arrows simply tell you that the fluid is flowing from left to right, and the magnitude of the arrow is the velocity. It is 0 at the wall and goes to u infinity, and if you look at the upstream profile here, the upstream value is also infinity. So, this is what you see if you measure the velocity profile. So, what you see is that the velocity varies rapidly from 0 to infinity over a thin layer close to the wall, and this region where the velocity gradients are large is called the boundary layer. And this point is not a line of constant y. I will draw by dotted lines the edge of the boundary layer. So, if I look at the velocity profile at this point, you will see that outside the boundary layer the velocity is u infinity, as in the case of this section, and here you are going to have a sharp variation. So, you can say this is say y equal to some delta x, where delta is the boundary layer thickness. So, this region we will call boundary layer. It is a layer close to the solid boundary. Now, I will take one of these profiles and plot it in a different way. Suppose I plot u versus y at a fixed x. So, I can call this x equal to say x1, and I can call this x equal to x2. So, if I look at u of x1 comma y, let us say this is a line which represents u equal to u infinity. The velocity is 0 at the wall, it increases, and then the velocity gradient decreases, and it will approach u infinity slowly at this. So, here I have plotted u versus y, whereas here I have indicated the plate, and actually we are plotting y versus u, that is on the vertical axis you have y and the horizontal axis you have u, but you are used to thinking in terms of graphs where the dependent variable is shown in the vertical axis. Now, the reason I am doing it this way is that if I want say del u del y at this point, then you will draw the tangent to this curve, and if I say the angle which the tangent makes with the horizontal is say theta, then you know that at this particular point, which is say y equal to some y 1. So, you look at del u del y at x 1 y 1, that is tan of this angle theta from the horizontal. Now, you can see that the largest slope is occurring at the wall, and at infinity the slope is 0 because the angle is going to 0. So, here tan theta is 0. So, this is the region where u is not changing with y, or del u del y is 0. So, that means that outside the boundary layer the shear stresses are going to be very small, and the fluid will behave like an inviscid fluid, although it is a viscous fluid, because the strain rates are very small, the shear stresses are going to be 0, as if it is a inviscid fluid with 0 viscosity. Now, if I consider the point y equal to y 1 here and draw the tangent, then del u del y will be tan of the angle from the vertical. So, I will draw another figure to enlarged figure to show this. So, this is y, and here I am plotting u. Now, if I take a point here and draw the tangent, and if I take the angle from the vertical here, suppose I call it alpha, then del u del y at this point P will be tan of the angle alpha. So, you can see that here the alpha is 0 if I take up tangent over here, because as you move in the y direction u is not changing. So, del u del y is 0 here, and the maximum del u del y here is going to occur at the wall. Now, if I look at tau x y, you know from Stokes' law of viscosity that for a Newtonian fluid tau is mu into del u del y plus del v del x. Now, we will show that in many cases the second term is small, much smaller than the first term. So, this can be approximated by mu del u del y. So, this justification we will discuss later, but what I am trying to say is that if you consider 2 points, say a point here say A and a point here say B, tau x y at point A is going to be approximately mu into del u del y at point A, and this may be a large quantity, definitely this is non-zero. But if you look at tau x y at the point B, which is approximately mu into del u del y at the point B, this you can say is approximately 0. So, we will use this fact that the shear stresses are 0 outside the boundary layer to get an approximate set of approximate equations which are easier to solve than the equations which I have already shown you. So, you can now define the boundary layer as the region or layer close to the wall where shear stresses are large, that is del u del y is large. And if you go to the region outside the boundary layer, which we will call the outer region, there del u del y is small and the shear stresses even for a viscous fluid where mu is non-zero here are almost 0. Now, let us come back to this integral approach which I was discussing. So, I have shown you 2 possible control volumes. Now, another control volume could be this one. One surface which is along the edge of the boundary layer, which I am calling y equal to delta x. So, at this point u is approximately u infinity, and at all points on this line over here you can say u is approximately u infinity and del u del y is approximately 0. All these 3 control volumes have one thing in common, that one surface coincides with the plate, because we want to find the drag on the plate. If you take a control volume which does not consider where part of the control surface does not cover the entire plate, then you will not be able to find what is the drag on the plate. Now, we will use this particular control volume today, and you can as a homework try the other 2. So, there is a plate and I will draw that control volume. Now, as I said, our origin is at the leading edge and x is along the plate and y is in the normal direction. So, this distance, vertical distance, we will call h naught, and this height we will call h. Now, h naught and h are not arbitrary because they are connected by a streamline. So, there is a relation between h and h naught. because we are saying that this is a streamline. Now, first of all, let us apply global conservation of mass. This will give you the relation between H and H naught. Now, if you recall the Reynolds transport theorem, for conservation of mass, you are going to have d dt of integral of rho dV over the control volume plus integral over the control surface rho v dot n dA. So, if I say that mCv is the mass of fluid in the control volume, then this what I have written over here is d dt of mass of fluid in the system which coincides with the control volume, and this part will be rate of change of mass of the fluid which is inside the control volume, and this is the net flux of mass from the control volume, and this will be equal to 0. So, this system is a closed system which occupies the control volume at time t. Now, we are taking a control volume which is stationary. So, the limits of integration here are independent of time. So, therefore, this d dt can be pulled inside the integral sign. So, the first term d dt of integral of rho dV we can write as integral over the region which is described as the control volume del rho del t dV. Now, if you have a constant density flow, then this del rho del t is going to be 0. If you have a compressible flow where rho is varying but is steady, then also del rho del t is 0. So, the first term is actually integral of 0 dV, and it is a definite integral. So, after you plug in the limits, this will be equal to 0. So, if we go back to the equation which I wrote earlier, the first term is going to be 0. So, the net flux of mass through the control surfaces must be 0. So, we will now look at this second term. So, here it is convenient to split the control surface into several parts. Suppose I call this surface 1, this surface 2, this surface 3, and this one top surface 4. So, let us look at the second term, which is integral over the control surface rho v dot n dA. This we can write as the sum of 4 integrals, integral over a 1 rho v dot n dA plus integral over a 2 rho v dot n dA plus integral over a 3 rho v dot n dA plus integral over a 4 rho v dot n dA. Now, v dot n may be 0 plus or minus. If we go back to this figure here, N2 is the outward normal here, N1 is the outward normal here, N3 is the outward normal here, and N4 is the outward normal here. Now, N1 is a constant which is minus I, N3 is a constant which is plus I, and N2 is a constant which is minus j. N4, because this is not a constant vector, it is changing because as you move from this point to this point, because this surface is a curved surface. Now, let us write down the signs of these quantities. So, I will draw that control volume again. This is my surface N1, sorry, the outward normal is minus I, and the fluid is fluid velocity will be in this direction. So, here V dot I minus I is going to be negative. So, this quantity is minus on surface 1. Now, on surface 3 your N3 is plus I. So, V dot N is going to be positive. So, this is plus. So, in the first case the minus sign signifies that mass is entering the control volume, and the plus sign emphasizes that the mass is leaving the control volume. So, you have to recall the fact that n is the outward normal. So, V dot n is the mass flux, mass efflux from the surface, that is, if it is positive then the mass will be leaving the control volume, and if it is negative it will be entering the control volume. Now, this one the surface 2 is an impermeable surface. So, the normal velocity will be 0, this we have discussed earlier. So, therefore, V dot n on this surface will be 0, the reason being A2 is an impermeable solid surface. Now, let us come to the surface 4. So, if you look at the surface 4, it is a stream surface. So, the velocity vector is tangent to it, and the outward normal N4 at any point is going to be normal to the velocity vector. This angle is 0. So, V dot N4 is magnitude of V into magnitude of N4 into cos of 90, which is 0. So, this is going to be 0. The reason is that A4 is a stream surface. Now, you can see the advantage of choosing a control volume where one of the surfaces is a stream surface. There will be no flux of property through that, because there is no mass flux through it. So, if you want to find flux of any property, you have to integrate it over the control surface, and there will be 4 terms like this, and only the integral over area A1 and the integral over area A4 will give you non-zero contributions to this. The second middle term will always be 0 because the plate is impermeable, and this term is going to be 0 because it is a stream surface. Now, I will draw the velocity profiles. This is the velocity profile here, and at the leading edge your velocity profile is going to be uniform. So, if you look at V on surface 1, this is one surface 1, that is u infinity I, and n 1 is minus I. So, v dot v 1 dot n 1 is minus u infinity. Now, what we want is this integral rho v dot n over a 1. This is one of the integrals we want. Now, for us rho is a constant. So, this is rho into minus u infinity, and if you take a small area element dA over here, that is going to be dy into, if you take a width b in the z direction, we can call it b dy, and then you have to integrate it from 0 to h naught, because this point we said is y equal to h naught. Now, these integrals, the function you are integrating here is a constant. So, this is simply minus rho u infinity into b into h naught. B into h naught is the area of the face. So, this is rho times the velocity times the area, and the minus sign is coming because it is a influx of mass. Now, similarly, if you look at the other integral rho v dot n dA, you are going to have this is the surface we call 3. So, I am sorry, I should call it 3 A 3. So, V 3 is u into I. You can call it u 3, or I am simply calling it u, or you can say u of x L comma y, where L is the length of the plate, and n 3 is plus I. So, v dot n is now u of L comma y, and dA I can write as b dy. Okay. Now, I have to integrate from 0 to h, because this point is h equal y equal to h. Now, this u is varying with y. So, you cannot pull it out of the integral, but you can write it as rho b integral of 0 to h u of L comma y dy. Now, the sum of these two has to be 0, because we have seen that integral over the control surface rho v dot n is 0. So, therefore, the algebraic sum of the first integral and the second integral, which I have written in these two equations, have to be equal to 0, which means that minus rho u infinity b h naught is equal to rho into b integral 0 to h u of L comma y dy. Sorry, this plus this equal to 0. So, this one you can also write in the form that rho u infinity h naught into b is equal to integral of rho b u L y dy. So, the left hand side is the net mass flow rate into the control volume through the surface 1, and the right hand side is the net mass flow rate leaving the control volume through the surface 3. So, mass flow rate in is equal to mass flow rate out. This is another way of looking at it. Now, since rho and b are constants, they cancel out. And we can write h naught as 1 upon u infinity integral 0 to h u of L comma y dy. So, this is the velocity variation at x equal to L with y. Now, E infinity being a constant, I can pull it inside the integral and write it in a compact fashion like this 0 to h u of L y by u infinity dy. So, this you can view as a sort of non-dimensional x velocity u by infinity at x equal to L. If you integrate this with respect to y from 0 to h, you get h naught. So, this is the relation between h naught and h. H naught is integral 0 to h u by u infinity at x equal to L and y dy. Now, before we proceed further, I will introduce a concept which is called displacement thickness. So, this is related to the displacement of the bounded streamlines. So, if you look at go back to the figure which we had earlier, this is the plate and we had a control volume where one surface was the stream surface. So, the plate is y equal to 0, this point here is y equal to h and this point is y equal to h naught. So, what you see is that the streamline has been displaced outwards by this amount which you can call d. So, d is h minus h naught. Now, we have already found a relation between h and h naught. So, we can write d as h minus integral 0 to h u by u infinity dy. Now, h I can write as integral 0 to h dy, and this I can write, this is as I leave as it is u by u infinity L y dy. Now, I can club it together and write it as integral 0 to h 1 minus u of L y by u infinity dy. Now, I will show the typical variation of this quantity. So, let us say I plot quantities versus y. If I plot, if I say this is say u infinity and this is 0 0, u by u infinity will go to 1, sorry. This is a typical profile u by u infinity. It starts with 0 at the plate and goes to 1 at infinity, because u is u infinity as y goes to infinity. Now, if I want to plot say 1 minus y by 1 minus u by infinity, you are going to have a curve which starts with 1 and goes down to 0. So, this is a curve 1 minus u by u infinity. Now, you can see here that this quantity which we call d, the displacement of this streamline outwards, is 1 minus u by infinity dy from 0 to h. So, you can interpret it as the area under the curve. Suppose I say this is my h, then that d will be this area. Now, I will draw that plate again, and let us say this is the velocity profile. This dotted line is the edge of the boundary layer. Suppose I take 2 points or 3 points, say A, B and C, or I can call them say 1, 2 and 3. I can draw the streamlines through this. All these streamlines are going to be displaced outwards, but by different amounts. So, this one suppose I say is H 1, this is say H 2 and this is say H 3. So, the first what I drew here, let me call H 1 and H 2 might be somewhere here and H 3 might be somewhere here. So, if you look at this quantity d, d 1 will be integral 0 to H 1 minus u by u infinity at L y dy. So, that is the shaded area. If I look at d 2, the amount by which the streamline through 2 has been displaced, it is going to be integral 0 to H 2 1 minus u by u infinity at L y dy, which I will show as this area. So, you can see that d 1 and d 2 are going to be different, and so if you look at H 3, you are going to get the area under the entire curve. Now, if I take a point 4 here, you will see that d 4 and d 3 will be the same, because the area under the curve has now converged to a certain value. So, what you see is that if you take this point to be outside the boundary layer, then the displacement of the streamlines are going to be constant. So, if I take 2 streamlines which are outside the boundary layer, these 2, they are both going to be displaced by the same amount, and that is what we call displacement thickness. So, displacement thickness we will call it delta star. This is a function of x, not of y. In general, here what I have done is I have looked at delta star at x equal to L, but you can do a similar analysis at any x. You can call it integral 0 to infinity 1 minus u of x y by u infinity dy. So, this gives you a measure of the amount by which the streamlines which are outside the boundary layer are displaced. Okay. And now, you can see why I chose this particular control volume over the other two, because this helped in introducing the concept of displacement thickness. Now, let us go back and complete the problem of finding the drag on the plate. Now, if you recall the Reynolds transport theorem, you are going to have rate of change of property for a system, that is rho phi dV. Okay, so, we will call it say R system maybe. This is equal to rate of change of the property for a coincident control volume plus the net flux of property through the control surface. So, when we applied the global conservation of mass, we had taken phi to be 1. Now, we will take, if you want to look at the x momentum equation, we will take phi to be the x velocity, which we are calling u. So, you are going to have d dt of integral over the control volume rho u dV plus integral over the control surface rho u v dot n dA is the sum of the forces acting on the fluid which occupies this control volume at time t. So, the left hand side is the rate of change of momentum of a system which occupies the control volume at time t. Now, if you look at the first term d dt of integral over the control volume rho u dV. Now, once again we are choosing the same control volume. So, limits of control limits of integration are fixed. So, this d dt can be pulled inside the integral. I can write it as del del t of rho u dV, and this quantity is going to be 0 because the flow is steady. Rho may be a constant and u is a function of x y only, it is not a function of time. So, if you take the partial derivative keeping x y fixed, then it is going to be 0. So, if you integrate 0 dV, you are going to get 0. Now, we have to evaluate the net flux of momentum through the control surface. So, we will look at integral of over the control surface rho u v dot n dA. Now, once again we will write it as a sum of 4 integrals. We have divided the control surface into 4 parts. So, you can write it as integral over a 1 rho u v dot n dA plus integral over a 2 rho u v dot n dA plus integral over a 3 rho u v dot n dA plus integral over a 4 rho u v dot n dA. I will draw the control volume again. This is a plate. You have one surface through which fluid is entering. So, this we called surface 1 and the outward normal was n 1, which is minus I. Outward normal to this surface 2 is n 2, which is minus j, and then you have a surface 3 through which mass is leaving the control volume. The outward normal is n 3, which is plus I, and then you have this stream surface which is a curved surface. So, the n 4 is varying from point to point. Now, let us write down the first of all look at these 4 integrals and see if some of them are 0. Now, this green line here represents the plate which is an impermeable solid. So, the mass flux through the plate is 0 at through any elemental area dA. So, you are going to have v dot n 0 because it is a solid impermeable substance surface. So, you are multiplying rho u by 0 and then you are integrating. So, this integral will be 0. Now, similarly, if you say that this surface is a stream surface, then at any point the velocity vector is going to be tangent to it and that is going to be perpendicular to the normal vector. So, this quantity here is going to be 0 because it is a stream surface. So, when you find the net flux of x momentum through the control volume, you see that only these 2 integrals are going to contribute. And before we find the values, let us look at the signs. So, u is positive here, u is also positive here, but if you look at v dot n, it is negative here because this is an influx and this is positive here because this is an out flux. The reason it is negative here is that n is pointing in the direction which is opposite to the flow direction. So, velocity vector is in this direction. So, the angle between V 1 and n 1 is 180 degrees. So, cos 180 is minus 1, and here the V and the n 3 they are in the same direction, the angle is 0. So, cos 0 is 0, and you have this to be positive. So, plus into minus, this will give you a negative contribution. So, that will represent influx of momentum, x momentum into the control volume, and this will represent outflux of momentum. So, on A 1 you can say that V 1 is u infinity I and n 1 is minus j. So, V 1 dot n 1 is minus u infinity I dot I, which is minus u infinity. So, therefore, integral over A 1 of rho u V dot n dA one can write as integral over rho u is infinity, and this is minus u infinity. And if I take a small area element here dA, that can be written as dy into the width in the z direction, which I am calling b, and then you integrate from 0 to h naught, that is the range of y for this surface. So, this will simply be minus rho u infinity squared into b into h naught. So, b into h naught is your A 1, the area of this surface. So, it is minus rho into the velocity squared on the surface 1 into the area. So, that is the first integral. Now, let us look at the second one, or rather the third one. Integral over the surface A 3 rho u v dot n dA is what we want to find. Now, on A 3 v we are saying is u at say x equal to L y I. Now, you are also going to have a small v component L y j, and if you look at the vector, so this is your V 3 n 3, that is going to be plus I. So, if you look at V 3 dot n 3, you are going to have u of L y I dot I plus v of L y j dot I. Now, this term is going to be 0, because the angle between I and j is 90 degrees, and this quantity is going to be 1. So, this is simply u at L y. So, this integral which you want to find will be integral of rho u into u. V dot n is nothing but u. Of course, this is u at x equal to L, and this we can write as dy into b. Now, you have to integrate from 0 to h. So, to be more precise, this quantity integral over A 3 we will write as rho u v dot n dA is equal to rho b integral 0 to h u squared at x equal to L y dy. So, this represents the flux of moment x momentum out of the control volume through the surface, which we are calling 3. Now, if we go back and look at this net flux, we have found these two terms, one was minus, the other was plus. So, if you want to summarize this, you are going to have integral over the control surface rho u v dot n dA. So, physically this represents the net flux of x momentum through the control surface. This is going to be minus rho u infinity squared into b into h naught plus rho into b into integral 0 to h u squared at L y dy. Now, if you go back and look at the mass balance which we have done earlier, we have come up with this relation that U infinity into H naught is integral 0 to h of u L y dy. So, that is another thing we can use. So, here there are two unknowns, one is h, other is h naught. So, we want to express one in terms of the other. So, we have seen that u infinity times h naught, this physically represents the volume flow rate into the control volume through the surface 1. This will be equal to integral 0 to h u of L y dy. So, this represents the volume flow rate leaving the control volume through the surface 3. Of course, these are the volume flow rates per unit depth in the z direction. To get the actual volume flow rate, you have to multiply both sides by b, which is already over here. Now, this first term here minus rho u infinity squared b h naught, I can write as minus rho b u infinity into e infinity h naught excuse me, and then u infinity into h naught I can replace by this integral. So, I can write it as minus rho b u infinity integral 0 to h u of L y dy. Now, this was a simpler expression, but we are replacing this by this integral, because we want a compact expression where we have only h as the upper limit of integration. Okay. Remember, for each h there is a h naught, they are not independent quantities. The reason being that those 2 points are connected by a streamline. So, therefore, there has to be a relation between h naught and h. Now, if I substitute this over here, we are going to have integral over the control surface rho u v dot n dA, and I would like to emphasize that this quantity represents the net flux of x momentum through the control surface. This I can write then as rho b, which can be factored out, integral 0 to h u squared L y dy minus rho b u infinity into this integral u of L y dy. So, we will club these two integrals together into one term and write it as rho b integral 0 to h, and then you are going to have the function which will integrate will be u square minus u infinity into u. So, that I can write as u of L y into u of L y minus u infinity dy. So, this quantity you can sometimes call the sometimes referred to as the momentum defect. Now, we have also studied inviscid flows. So, we will look at right now say an inviscid flow. For inviscid flow, if the upstream profile is a uniform profile and the plate is aligned with the direction of the flow, it is not going to alter this flow, and the profile at any point will remain the uniform profile here. So, if you want u L y here, it is going to be this u infinity everywhere. In that case, this moment of defect is going to be 0, because this u L y will be u infinity everywhere. So, you have u infinity minus u infinity, which is 0 dy, and that is the reason why you will find that for inviscid flow the drag is 0. Now, for viscous flows there will be a net force. So, this will not be 0. Now, we have to find what are the forces on the fluid which is inside the control volume. Forces on fluid inside the control volume. So, I will draw the control volume again. This is the plate and you have one surface on the plate. Now, what we would like to do is take a system which at time t occupies this control volume. So, this is a system which in thermodynamic terminology is a closed system at time t. Now, what we will do is we will show what are the forces which are acting on this. So, this is what we will call the free body diagram of this. Now, we are interested in the x momentum balance. So, for simplicity I will write only, I will show only the forces in the x direction, or the forces which will contribute to a net force in the x direction. Now, if you look at this surface, there is a fluid on the left of this surface which is going to push the fluid which is inside the control volume, and there is going to be a distributed load here which is the pressure. So, this is not the velocity, but the pressure at section 1. Okay. Now, this fluid on the right side of this also is a continuous mass of fluid which is flowing, and that is also going to exert a force on this. Now, the normal stresses are compressive. So, this will be a distributed load like this. Now, we are going to assume that these two pressures are the same, and this could be identified with P infinity. We will show that the variation of pressure in the y direction is negligible. Right now, we are going to assume it. So, that is why you do not have a pressure profile here, but a uniform pressure distribution, and we will show that using order of magnitude analysis that this also is going to be the same as P infinity. And you are going to have a force which is going to act normally here on this surface, that also will be the same as P infinity. So, these are assumptions which we are making for the timing, we will justify it later. So, what I have shown is the surface force here, the surface force here, and I have not yet said whether this streamline or this stream surface is inside the boundary layer or outside the boundary layer. So, if it is inside the boundary layer, then you have to consider the shear stresses also, because this could also contribute to the net force in the x direction. Now, you are going to have shear forces here on this bottom surface. I am not going to indicate the pressure force on this bottom surface, because that will not contribute to the x direction force. Recall that this is x and this is y. Now, or if you want, you can show the forces. Now, the gravity, if I say that this is gravity, then the gravity force in the x direction component also is 0. So, these are the net forces. Now, this force here, if I integrate it, you will get the drag on the plate. So, if I say drag on plate is a d, to get the drag, Now, we will assume intuitively that the drag is in the direction opposite to the direction of flow. So, this is the net resultant of those shear stresses. Now, after we do the calculation, if you find that d is negative, then we will know that the drag is in the opposite direction. So, this is the force exerted by the plate on the fluid. The force exerted by the fluid on the plate will be in the positive x direction if this is, if d turns out to be positive. So, if I say tau wall is the magnitude of the shear stress at the wall, so this will say is tau wall this of x, because it will vary with x. Then d you can say is integral 0 to L tau wall x dx. Now, let us look at the other forces. Let us look at the net pressure force first. Now, if I say this length is h naught and the pressure here is a uniform pressure value P infinity, then this will be P infinity into h naught into B, where h naught into B is the area of the face 1. Now, on face 3 also, if I say this is P infinity, now note that it is acting in the opposite direction. So, you are going to have a contribution minus P infinity into h into B, where h is this height. Now, to find the force here, you have to look at the component of force due to pressure in the x direction. So, if I say this angle is theta, angle which this surface dA is making with the horizontal is theta, then the angle which the pressure force will, this is P infinity dA, makes with the horizontal, sorry, with the vertical will also be theta, and you can see that it is acting in the positive x direction. So, this is going to be plus integral of P infinity dA into sin theta. So, this P dA has a component in the negative y direction, which is P dA cos theta, and a component in the x direction, positive x direction, which is P dA sin theta. Now, this dA, let me draw another figure here. Suppose I say this is my curved surface, but I have a small area element. So, this surface dA is tangent to this curved surface. So, if I say this length is dl, then dA is going to be dl into the width in the z direction. Now, I can draw this triangle over here. This is going to be dx and this is going to be dy, and this angle is theta. If you are getting confused, I will draw another enlarged view. Let us say this is dl, this is dx, and this is dy, and this is theta. You will see from here that dl sin theta is dy and dl cos theta is dx, but we do not need it. Now, dA is dl into B. So, let us look at this term integral of P dA, P infinity dA sin theta over the surface A3, sorry A4, which is the curved stream surface. So, this is going to be integral of P infinity dl into B into sin theta. Now, dl into sin theta is dy from this relation. So, I can write this as integral of p infinity b dy. So, this is the surface which we are calling 4, and we are integrating from this point to this point along the surface. So, y is going from h naught to h. So, this is going to be equal to integral from h naught to h p infinity b dy. Now, p infinity and b are constants. So, simply this is simply p infinity b integral of dy from h naught to h, which is p infinity into b into h minus h naught. So, let us come back and look at this balance equation over here. This quantity over here we have found to be p infinity into b into h minus h naught. Now, you see that, so this quantity F pressure net. So, this is the net pressure force on the system which occupies the control volume at time t in the x direction is p infinity h h naught into b, that is the first term. This is the net pressure force on the surface 1 minus p infinity h b, that is the net pressure force in the x direction on surface 3, and then you have p infinity b h minus h naught, which is the net pressure force in the x direction on the surface 4. Now, the net pressure force on the surface 2 is in the y direction. So, we are not considering it in the x force balance. Now, you see that this term and this term will cancel out, as will the other two terms. So, the net pressure force here turns out to be equal to 0. This is equal to 0. So, this of course, is with the assumption that the pressure is uniform, which we have for the timing is an assumption, but in the afternoon session I will discuss the boundary layer approximation and justify that. So, let me just write down the final equation. You had ddt of integral of rho u dv over the system, integral over the system region is the sum of forces in the x direction. So, this we had found as what we call the momentum defect, which is this quantity. So, you are going to have rho times b integral 0 to h u of L y into u of L y minus u infinity dy. This is the net momentum change of the fluid, and you can anticipate that this term is going to be negative, because this is plus and this is minus. So, this will be the net force acting on the fluid in the x direction. So, that is minus d, which is the drag on the plate, and the minus sign is coming because of the assumed direction, and then you have the F pressure net in the x direction, which we have shown to be 0 under the assumption that it is a constant pressure boundary layer. And then you are also going to have a viscous force net on surface 4 in the x direction. So, this will come from the shear stresses acting on the surface 4, and of course, since the net force in x direction, you also have to take the appropriate component of that. Now, what we will do is we will assume take the limit when h is very large. So, when h is large, the shear stresses on the surface 4 will be 0, tau x y on surface 4 will be 0. So, F viscous net, the net viscous force on the surface 4 x component will be 0. So, provided h is large enough, so that the stream surface 4 is in the what we are calling the outer region, that is entirely outside the boundary layer, you have a relation that the momentum defect is minus d, and the function you are integrating is going to be negative, because this quantity is plus and this quantity you expect to be minus, because u is less than u infinity inside the boundary layer. So, product of these two is negative. So, when you integrate a negative quantity, limits of integration are positive, you are going to get a net quantity which is negative, which will cancel with this minus sign over here. So, you will get d is rho b into u infinity minus u. So, you have this relation that d is rho b integral 0 to h u of L y into u infinity minus u of L y dy. And I would like to remind you that this quantity is plus, because u is less than u infinity, less or equal to u infinity, and this quantity is also plus. So, therefore, our intuition is correct that the net force exerted by the plate on the fluid inside the control volume is in the negative x direction, which means that the force exerted by the fluid on the plate is in the positive x direction. Now, this is a very useful relation, and if you measure the velocity profile, say, and carry out a numerical integration, you can estimate what is the drag. So, let us say this is a plate of length L. In the lab, you measure the velocity at different points in the y direction at x equal to L. So, this is a plate, and you may get a profile which is like this. You can do a graphical integration or a numerical integration to estimate this, and you will get the drag on the plate. So, we will take a break, a lunch break for 1 hour, and then we will come back to